It's good.
Okay.
Good.
Designing innovation has more to do with pushing the envelope of what is possible and needed, rather than swimming in the status quo. Design follows function, and the results, well, they can be amazing.
AirShip Technologies Group is a design and manufacturer company for unmanned aerial vehicles. What's unique about AirShip, we are building long flight endurance, clean tech propelled drones.
Welcome to the 39th Annual Pacific Northwest Software Quality Conference. I hope you all are having a great time and enjoying yourselves. It is a pleasure to speak with you today. My name is Ben Berry. I am the CEO for AirShip Technologies Group. In my business, managing mission-critical products in flight is about high-speed VTOL, vertical takeoff and landing, autonomous aircraft that are integrated with two-stage launch rockets to deliver microsatellites into low Earth orbit. From the liftoff to the flight control autopilot, software can be found almost everywhere in our avionics systems. And to ensure the safety of the mission and the aircraft, aerospace software applications must be vigorously tested within strict FAA guidelines to ensure that they all operate correctly. So, failure of onboard critical software, be it both safety critical and or mission critical, could have far-reaching repercussions. Avionics systems comprise many thousands of functions and millions of lines of code. But in terms of launching our two-stage rockets from our AirShip VX-24 multifunctional autonomous transport, we must ensure safety of the system. It must be tested and retested to make sure all components operate as expected. And why is launching small satellites so important? Well, because in the next big war, first-generation satellites will be destroyed and need to be augmented now with much smaller microsatellites that deliver even more capabilities. In fact, the U.S. Air Force believes that many of the runways will be also destroyed in the next big war, and they are insisting that the new high-speed transports be capable of carrying large payloads and be capable of vertical takeoff and landing, better known as VTOL. So why and what do we see in today's marketplace? Well, SpaceX is launching large-scale satellites pretty much on a weekly basis, but that's really a good thing for us. As our world gets more and more connected, we use satellites on a daily basis, whether you realize it or not. But launching a three-stage rocket from the ground is no small task. It's a massive effort that not only requires a ton of equipment and fuel, but thousands and thousands of hours of labor power. Well, the Space and Missile Systems Center, element of the U.S. Space Force, AirShip Technologies Group's VX-24 unmanned aerial system is a reusable air platform for high altitude and two-stage rocket launch for payload placement of 5G communications. So something has to change. Switching from ground-launched three-stage rockets to two-stage rockets, aerially launched from a reusable high-speed autonomous drone, makes a lot of sense. You know, when I worked at Hughes Aircraft Company in Los Angeles in 1991, I attended UCLA and their executive MBA program. One of the class assignments I had was to examine how self-managing teams at Hughes built, operated, and software tested large-scale satellites. But today, satellites have gotten much smaller. So we are pairing our VX-24 transport with a payload of 12 rocket launchers aimed at space. With the speed of the VX and the two-stage rockets, the plan is to hit the 17,600 miles per hour rocket speed to reach low Earth orbit and disperse our payload of small satellites. Satellite communications resiliency is made possible via high-altitude launch of the two-stage rockets that deliver 5G-enabled smaller and smaller satellites. And this small sat drive to miniaturization is really impressive. Here you can see where the satellite industry began with large sat Hughes aircraft-style satellites to progressively smaller satellites, all of which require software and quality checks. For example, deployment of satellite communications, known as SATCOM, enables 6 to 12 nanosats, or 100 picosats, or 1,000 femtosats per flight sortie of our VX-24, designed as a multifunctional drone transport. Satellite cluster designs may be launched individually, or they may have multiple nanosatellites working together or in formation, in which case sometimes the term satellite swarm or fractionated spacecraft may be applied. Some designs require a larger mother satellite for communication with ground controllers or for launching and docking with nanosatellites. And to date, over 1,300 nanosatellites have been launched as of January 2020. With continued advances in miniaturization and capability of electronic technology and the use of satellite constellations, small sats are increasingly capable of performing commercial missions that previously required large satellites. Technology just keeps getting better and better, smaller and smaller. The VX-24 autonomous drone's advanced just-in-time launch capabilities give America's defense efforts a huge competitive advantage over our competitors, the Russians and the Chinese, who are investing in similar aerospace technology. Software-tested design objectives include aircraft flight deployment and reuse, interconnected 5G mesh communications, exploitation of the ultimate high ground of space communications, and space-empowered SATCOM data link resilience. The VX-24 air vehicle supports defense and commercial sectors while extending and optimizing use of secure, interoperable networks and enabling command and control space communications. This mission, three important software testing and quality protocols emerge. Number one, functional testing. This is to ensure that software programs match both high and low-level requirements criteria, basically that the software functionality works as designed. Number two, time analysis of worst-case execution. There are certain time-critical lines of code, and it is crucial to test that they operate in the desired weight within a specific timing restriction, especially between rocket launch, rocket stage separation, and small sat suborbital dispersion. And finally, number three, analysis of structural coverage. This ensures that the structural parts of the software code is tested and validated to a certain degree that is acceptable by FAA industry standards. Software component traceability testing includes airborne systems traceability testing, operational environment quality testing, and satellite communications software testing. For the airship hardware and software component traceability assemblies and testing, the Alpha Drive high-speed VTOL propulsion was invented to allow for aircraft runway independence. The VX delivers the Alpha Drive propulsion system for transitioning from vertical takeoff and landing to fixed wing flight within a moment's command, and its components are quality checked and assemblies traceable to original equipment manufacturers. There is no tilt rotor arm scenario or rotors hanging off the ends of wings. The VX high-speed VTOL combines airship's Alpha Drive thrust transition, airframe innovation, and integrated jet propulsion, enabling flight to an altitude of 30,000 feet to launch its two-stage rockets. The Alpha Drive carries our U.S. patent and supply chain, and the Alpha Drive aeronautical capabilities include top and bottom wing integrated dual thrust iris dampers to create super compressed air thrust. The air vehicle flies with lateral turboshaft engines housed in the lower fuselage of the aircraft that power the VX lateral ducted propellers mounted on titanium engine mounts. There are 920 manufacturing segments with thousands of assemblies and components and subcomponents to manufacture and test the VX-24. VX airborne systems such as flight controls, avionics, and engine control are typical examples of safety-critical real-time systems. These systems are extremely software-intensive and complex. The VX operates in environments with diverse ranges of temperature, humidity, air pressure, vibration, and movement, and are subject to the effects of age, maintenance, and weather. Typical characteristics required of such systems are reliability, fault tolerance, and deterministic timing guarantees. The construction and maintenance of the VX involves a variety of products, including wide bandwidth amplifiers, high voltage connectors, electromagnetic interference EMI filters, hybrid gas to electric converters, laser rangefinder receivers, onboard computers, lighting, communication systems, and solid-state serial bus interfaces. These products, along with parts and supporting equipment and subsystems, are designed and manufactured by dozens of companies and different specialties. One thing all of these suppliers must have in common is a concern for quality and compliance. And to satisfy quality requirements of the U.S. Department of Defense, the DoD, the National Aeronautics and Space Administration, NASA, and the U.S. Federation Aviation Administration, the FAA. Suppliers to the VX program must be able to trace all components of a failing part back to its origin. To do this, they ultimately hold suppliers accountable for providing reliable products. Suppliers must have the ancestry of those components on file. AirShip uses software failure mode and effects analysis as a technique to identify potential software design or deep dive process problems. The method examines causal relationship and effects of lower level failures on aircraft components and systems. There are 4 ways to measure the impact of a software failure mode. Step 1. Identify potential software failures and effects by analyzing the functional requirements and their effects to identify all failure modes. Step 2, determine severity. Severity is the seriousness of failure consequences. Step 3, gauge likelihood of the failure occurrence. And finally, step 4, detect a failure. Software communications architecture, the Flight Command Center provides reliable operation of communication systems, navigation equipment, and radar detection systems. The radio frequency interference between systems must be managed through design, system integration, and testing. Adhering to compliance standards for radio frequency systems is a legal requirement for authorization to operate an air vehicle. The certification bodies like the U.S. Federal Aviation Administration and the European Aviation Safety Agency stick to software considerations related to DO-178C set out in the certification program. The guidelines for airborne systems and equipment is the approval process for software-based aerospace systems. The guideline works to ascertain that critical and operational software involved in airborne systems are operating as desired and are not a threat to safety. Therefore, investing in a reliable and independent quality assurance service provider to conduct proper safety compliance testing is essential to ensure avionics systems operation and security. The triad of aerospace safety and quality, navigation, communication, radar detection, are key to keeping the VX airborne and for meeting the autonomous VX transport mission. In aviation, the Instrument Landing System, the ILS, is a radio navigation system that provides short-range guidance to the VX to allow it to approach a landing zone or runway at night or in bad weather. In its original form, it allows the VX to approach the landing zone until it is 200 feet over the ground and proceeding to land. Space-based global positioning satellites, or simply GPS, carry atomic clocks that provide extremely accurate time. The time information is placed in the codes that are broadcasted by the satellite so that a receiver can continuously determine the time and signal of the broadcast. Thus, the receiver uses 4 satellites to compute latitude, longitude, altitude, and time. As a partner to the AirShip VX program, we use the COSAR Corporation subsystem module to provide a low swap, or better known as size, weight, and power, solution to provide a timing holdover when a GPS environment is denied or interrupted. The very high-frequency VHF communication system is used for maintaining contact between ground control and the VX drone. This employs line-of-sight transmission, which translates to a range of about 30 miles for the VX operating at 1,000 feet above the ground, or 135 miles with the VX operating at 10,000 feet. Airborne weather radar is used to provide an indication to the VX Autopilot of the intensity of convection weather. Convection is a term heard quite often in meteorology. In weather, it describes the vertical transport of heat and moisture in the atmosphere, usually from a warmer area, the surface, to a cooler one, airborne. Glide slope provides the instrument landing system for a precision runway approach, or VTOL landing, where 2 radio beams provide the VX Piccolo autopilot with vertical and horizontal guidance during a landing approach. The localizer component provides azimuth guidance for forward track navigation, while the glide slope defines the correct vertical descent profile. And finally, the distance measuring equipment, DME, is a radio navigation technology that measures the slant range distance between the VX and its ground station by timing the propagation delay of radio signals in the frequency band between 960 and 1215 megahertz. As an autonomous drone aircraft, the AirShip VX is controlled via the onboard Piccolo Autopilot and a communications interface to the customer's control center. Its extensive flight planning and management software allows for up to 1,000 GPS-enabled waypoints, aerial destinations, and vertical takeoff and landing insertions. The autopilot actually enables the VX change in airspeed, altitude, and heading. The highest opportunity for software testing and quality assurance is with the software interfaces to the Piccolo's terrain database that supports digital terrain elevation data and data from the Global Space Shuttle radar topography missions. These layers include map terrain warning layers and GPS flight waypoints, airspace boundaries, and contain aircraft flight geofencing. A squadron of VX-24 drones achieves flight swarms through the autopilot's protocol for flight route copy between multiple VX aircraft and can manage multiple aircraft simultaneously on a single mission, thus making possible the launch of multiple simultaneous flight sorties of two-stage rockets carrying hundreds to thousands of small satellites for defense mission or industry-specific use cases. The autopilot can change airspeed, altitude, and heading to deliver on the mission. In austere launch environments, the VX uses a terrain database and map terrain warning layer for setting airspace boundaries and creating a geofence over specified locations for vertical takeoff and landing and flight. Both China and Russia's GPS spoofing capabilities continue to advance and in some cases be deployed against rival forces in contested areas. And the U.S. military has been conducting exercises that simulate operations in GPS-denied areas. New jam-resistant GPS systems have already been software quality checked and installed aboard some U.S. military aircraft. And the military uses encrypted GPS technologies that are much harder to disrupt than civilian networks. Still, given that GPS relies on satellites, which are increasingly under threat from peer state rival space technologies, a future conflict that involves orbital warfare could see satellite-based GPS networks knocked out entirely. Hence, the need for a more versatile positioning, navigation, and timing of GPS-independent flight operations. For the high-level software and communications architecture, VX operations depends on a control center as the ground control station. This is considered a multifunctional operations center known as the Mach 1. Using artificial intelligence and communication software, the vision for control center personnel is that they are responsible for Earth and Space C2 command and control of multiple VX-24 transports serving various missions globally. The onboard DAA detect and avoid payload interface manages collision avoidance for both the VX and the launch of the two-stage rockets. Encrypted C2 command and control protects the air mission from interruption, and the ground control stations manage the Global Launch Vehicle Center distributed communications and operations environment. But that's not all. Enter the Automated Dependent Surveillance Broadcast, or for short, ADS-B, as well as the radar that tracks the air vehicle and launch rockets. It allows both controllers and the onboard autopilot to get an accurate picture of air traffic. But ADS-B provides data on more than just aircraft. When a rocket is launched, the airspace system requires considerable advance notice in order to close the airspace affected by the launch and issues notices to other nearby aircraft. The FAA launched ADS-B in January 2020 and enables a much more seamless integration of air traffic and space launch activities. ADS-B shifts aircraft separation and air traffic control from ground-based radar to satellite-derived positions. ADS-B outbroadcasts an aircraft's wide area augmentation system, enhanced GPS position, to the ground, where it is displayed to air traffic controllers. It's also transmitted to aircraft with ADS-B receivers, either directly or relayed by ground stations, increasing the VX autopilot situation awareness. For software failure, detention, and accommodation, we test and optimize the VX variable pitch propeller blades. The VX's variable pitch lateral propellers are controlled wirelessly by the Autopilot and can adjust blade pitch during flight. For vertical takeoff and landing, propeller blade pitch is positioned for lift. In full throttle forward flight, the alpha drive top and bottom irises close, and the internal blade pitch changes from maximum lift capacity to maximum contained air compression for intake to exhaust high-speed thrust. The blade angle adjusts to the optimum value for the phases of flight. For example, takeoff and landing, full throttle climb, cruise, or hover. Combined with VX alpha drive thrust and the rear-mounted electric turbofan jets, the VX launches its two-stage rockets to achieve the 17,600 mile per hour climb to reach low Earth orbit and release its small SAT payload. In summary, even though test automation is a common and well-known way to reduce software testing workload, mathematical modeling has become another remedy. The AirShip VX program expects to employ a model-based approach and fuzz testing technology, where a simulation is created to show precisely how an aircraft will behave when a certain software is installed into the system. Fuzz testing is the process of bombarding the software system of the aircraft with random data to try and find its breaking point. As you can imagine, software encapsulates the aviation sector more than you might realize. It is no surprise that testing has become such an indispensable part of the industry. However, the process can be problematic given both the complication and volume of data to be dealt with. With more and more progress in testing, we at Airship Aerospace have to be on our toes to keep up with the requirements of the various systems we've discussed and our relevant solutions to make progress and survive in a rapidly changing global environment.
There's a familiar pattern in reinvention. Rethinking answers to problems lead to a new technology coming along to fill a long-standing need. But as it becomes widely implemented, questions arise over how best to use it and how it may change the rest of the world.
So that's the presentation today, Ying. I'm open to questions, Q&A.
Yeah, I'm going to take the chance to ask the first question. You emailed and told folks on the program committee that you enter a Air Force challenge. Can you tell us a little bit about that?
Yeah, about 6 months ago, Airship participated in the AFWorks challenge initiative by the U.S. Air Force and the SATCOM group in terms of developing a new technology, a new aircraft that would be made for high-speed vertical takeoff and landing, but also have the capability of a large payload. This particular requirement was for 20,000 pounds, which is what the VX aircraft is designed to do. There were 216 companies that applied in this initiative. We went through online presentations to about 25 Department of Defense people. Then we went to Las Vegas. They took the 216 down to 39 companies. 39 companies went to Las Vegas, and we did a showcase of our technologies. From that, we whittled down to about 8 companies that will be given contracts, and Airship is a part of those 8 companies. Those announcements and awards are actually due out this week. There'll be multiple awards. I don't think it'll be all 8, but at least 4 or 5 awards. And we're just very, very excited about the progress that the team has put into developing the aircraft based on the requirements of the government. So that's where we are in terms of satisfying the need.
Well, that's congratulations to you and your team. It's quite a remarkable presentation by video that you made earlier. I'm just curious, among your development team, what fraction of the team are kind of like hardware engineers and what part are software engineers?
Well, we only have a team of about 12 people. We're spread out across the U.S. We're all working out of our homes. Most of the people are software engineers and aeronautical engineers. It's about 50-50 at this point. And we will probably, in the proposal, AirShip would be the prime, which will allow us to add more people. But we would be teaming with Lockheed Martin to do the heavy lift, doing all the aeronautical design work, the simulation work. The production in phase one is for the first aircraft to be produced, that over 18 to 24 months. And then phase two, 6 aircraft will be produced over a 2-year period. And from there, mass production to be farmed out either in an RFP that many of the largest size aerospace companies would be bidding. Lockheed, Northrop Grumman, that nature. And you might remember, Yang, when I worked for the state of Oregon, I was talking about this new aircraft vision called the AirShip. That takes us back quite a few years. I'm thinking, about 18 years?
Yeah. Obviously, you and your team has been at this for a long time, and you're of course quite well known in the Portland area. I'm not really sure folks from other parts of the country or the world. I'm happy to tell you that this conference have over 300 registrants, and with over 15, 16 countries outside of the US that are attending today.
That's amazing.
So it's a conference that we have tried very hard to add value to the software quality community. Now, your product, of course, has a lot of embedded software, and software, as you presented, is kind of a technological enabler for this type of system. We have a question coming in that's wondering. You started the presentation by talking about launching satellites, and clearly there's a lot of applications like reconnaissance and military and other civilian applications. In terms of civilian application, what might be some of those things that that you're kind of at greater liberty to talk about?
Yeah, I think with the initial thrust on this was really for a high speed, high altitude, vertical takeoff and landing transport. I mean, the closest thing the military has is the Osprey V-22. So we kind of patterned the requirements based on the 22, which is not a jet style aircraft. It's propeller based. It gets about 327 miles per hour. So on the commercial side, think about an autonomous aircraft like this being a substitute to the trucking industry. Think about all the trucks that are along the highway today. The internal dimensions of this aircraft are 14 feet wide by 14 feet high by 55 feet long. So that would, in fact, take a container. And with the shuttle bay doors on top of the aircraft opening very wide to the needed space, you could literally drop in a container within the body of this aircraft, still being able to accommodate that 20,000 pound payload to do the kind of commercial requirements that you're seeing in the trucking industry. And that's not for all kinds of needs of the trucking industry, but very specialized needs that have to get to market fast or get to a project or initiative very fast. So that's one of the commercial aspects.
Great. Obviously, with commercial, there's also the military aspects. Obviously, you mentioned quite a different kinds of military-related applications. I'm reminded, of course, in the last administration, there was the talk of the Space Force. Is any of this work pertinent to the work of the new Space Force?
Yes, part of the branches that would make use of this particular use case, delivering 2-stage rockets for satellite distribution, would be the Space Force. They're all about communications resiliency, especially given the example I gave that many of the large satellites would be destroyed in a large war. They need something that is so small that it's not practical to be able to destroy 1,000 small satellites that are very tiny. And so that's really where the Space Force's resiliency communications is looking to be satisfied. And this being a multi-purpose transport vehicle that could be outfitted with the rocket launchers to be able to launch those rockets would be another use of the aircraft. It's not the only use. There's some 60 different uses of this aircraft, mostly on the military side that we've examined that would make sense for that particular customer.
Well, that's kind of awesome. Maybe I'll move a little bit toward kind of discussion about innovations in general and not specifically about aerospace innovation. Obviously, in the United States, some of the greatest technology that we take for granted every day, like the internet, optical storage, many of these things come from research that was initially funded by the military. I'm just kind of curious as to what you think is the role of the military collaboration with industry in terms of creating not just better technology, but since we're a software group here, especially in the development of software-related technology.
Well, I'll use the example of the AFWorks challenge. Their goal was really to ask the marketplace, ask industry, what is possible given the kinds of things they want to do in terms of vertical takeoff and landing, high speed, heavy payload. They didn't want to specify specifically, from A to Z, the requirements. They really wanted these 216 firms to come back after listening to several, webinars that they had produced and deliver what we interpreted as a solution to go forward. So that the first thing that comes to mind is making reuse of our alpha drive technology that you've seen in these wings. That's a very new technology. I acquired about 29% of a firm called Alpha Sky that produces that technology. We are now partners. I own 29% of that company. And we incorporated the large size alpha drives with top and bottom irises, much like a camera lens where the iris closes and opens, to be able to contain the ongoing propellers as they move and turn them from the dimension of lift, which is a particular angle for lift, where we're slicing through the air to raise the aircraft or lower it, to actually wirelessly change the angle of the blades to become more of a compression blade as we close off these top and bottom irises, sucking in from the air intake and then releasing that super compressed thrust out the rear of the nozzles of these two lateral ducts. That technology alone, we believe, is a game changer in aerospace. We don't see that in aerospace. Every different ladder, the different kinds of aircraft that get produced, bring forth yet a newer and newer innovation that allows massive change, in this particular case, in the aerospace industry. So we're excited about that. And all of that does take software. I mean, it takes software to program these irises, to take software to be able to change to the angle, be it lifting or landing or full throttle or cruising or hover. All that has to work simultaneously so that we don't have any crashes. Safety is the number one paramount consideration when you think about aerospace and aviation in general. And we are right there with what this particular conference does. We're talking about software and quality analysts and management that are attuned to be able to deliver on the use case and the mission. But it all has to be tested, retested. We have compliance with the FAA, in this case with NASA, with the rocket launches. And all of that comes into play to be able to field, operate, and have the authorization to operate this kind of an aircraft. Give you an example of that. The Osprey V-22 took 18 years to actually go from the design to fielding hundreds of those V-22s around the world, the U.S. military and other countries. That's a long time to prove the technology. we suspect we will have a similar timing in terms of finishing all that needs to be finished to be able to field this and have the label of safe. It won't happen overnight, but every year that we are involved in this kind of development is another constructive case for building revenues and building safety and building jobs and acquiring more and more technical people.
And I have one parting questions. You have 30 seconds. Do you mind telling some of our younger participants how best they can advance their career?
Yeah, I think the best thing young people can do is figure out where their passion is. Where does your passion lie? We might see this aviation as, I'm really passionate because it looks cool. But it's an internal thing. And the way you discover your passion is to really get exposed to a lot of different technologies and services and businesses. And what you tend to like, that's a clue as to your passion. So if aviation, aerospace is something you got exposed to today, there are aeronautical degree programs. My dad was the first African-American to graduate in aeronautical engineering from USC. He was a Tuskegee Airman coming out of World War II. And that's where I got my focus and vision after talking with him for so many years.
Thank you so much. You're a very inspiring speaker, and I hope all of us have learned from your enthusiasm and your broad range of experiences. I am also very amazed, in case some of the folks didn't hear, you actually have a day job as the CIO and Senior VP of Bonneville Power Administration, which is a major federal agency.
That's right.
It's almost a hobby. It's an amazing hobby, and congratulations for all the great work that you've done, and the good luck with your Air Force competition. And I am now going to say goodbye to you and allow everybody to move on to the next session. Thank you so much for your time today.
Thank you. It's been my pleasure.